particular time, if you wanted to take the exam early, I'll answer them today probably. I think in terms of the overall thing, though, what I'm going to do, some people asked about having a review session early. I probably won't do that, but what I might do is have a bit of a review on Wednesday in class. And then, but then probably have a review session, possibly Wednesday night, but more likely Thursday. Anyway, I'll be sending an email probably tomorrow about that. Okay? Any other questions? All right. So I believe on Friday we didn't talk about this at all, right? So the next interesting thing to treat, we treated a barrier. We treated a particle hitting a potential, and whether or not the particle had energy above the potential energy or less than the potential energy, that's what we treated. But that potential just went off to infinity. Here's a more interesting case of a barrier. So a particle is going to come in, again, incident from the left. Here's x equals 0. It sees a region with a potential. It sees a region with potential, and then the potential's gone again. So this is a barrier. And there's going to be two cases. The first one I've sketched is that the energy of the particle is greater than the height of the barrier in that region. Okay? So we can treat this, again, you break it up into 3 regions, and we can just about, in fact I will, because I've practiced it a lot, simply write the following terms. In region 1, I know it's going to be straightforward. I'll have a wave coming in from the left to the right. I'll have a reflecting wave, and k will simply be that by plugging back into the Schrodinger equation, right? So you should be able to recognize that that's going to be the case. In region 2, certainly, if I don't know any better, I better write both of the terms that are possible. Right now, oh, sorry, I'm doing the wrong problem. It's not alpha. If the energy is greater than U0, fundamentally the Schrodinger equation is the same in all 3 regions. It's just that this potential energy term will subtract off from the energy as a constant when I rearrange the 2 terms in the Schrodinger equation. So this is just e to the ikx, well, I'll use a k prime. Okay, and I know this is down at the bottom of the board. Right. So k prime here is that, where it's based on the energy minus U0 instead of the energy alone. Notice, is k prime bigger than k or less than k? And does that have a physical meaning to you? It should, actually. It's less mathematically. What is k? It's sort of the inverse of the wavelength, the so-called wave number, 2 pi over the wavelength. So k prime being less, wavelength is bigger. In general, bigger wavelengths are lower energy states. That should sort of be in your head at this point. And psi 3, it can only be moving to the right unless I include some other thing way out to on the right that's going to reflect the wave. And we're not going to include that. So these are my 3 terms, my 3 waves. The k and the k prime are given. This is the same k again because energy U is 0 over there in region 3. and I have psi is continuous, and I have that psi prime is continuous, right? So you know the drill, right? At x equals 0, I have a plus b equals c plus d. Oh, should I back up a second? Right here, well, it's obvious here too that I needed waves both in region 1 and 2 to be going both left and right. Because here's the key point. Suppose I have waves, the particle somehow gets from the, not somehow, some portion of the particle, of the flux of particles go from here to here. Some is reflected, but some is transmitted. Even though this is a step downwards, and this is a key point, even though this is a step downwards, I could have a reflection at that juncture. Certainly, based on what you know, you shouldn't say that there won't be a reflection. I mean, in fact, even classically, in an electromagnetic wave, you can have a reflection back. I mean, I certainly think of the reflection when I'm coming from here to here, where somehow I'm going to have to convert kinetic energy into I'm going to lose kinetic energy and convert it into terms of potential energy. So it's sort of, there is a barrier. It's analogous to, rolling a ball and then it goes up a little bit of a hill. It will slow down, and if it's a wave, it's like, okay, it makes sense that it bounces back. Nonetheless, if it's going to roll back down the hill and pick back up its kinetic energy, there's still a chance that it will reflect back. Certainly when I'm treating this new quantum mechanical system, I'm not going to be allowed to just throw out the D based on some intuitive notion of that it ought not to reflect. Okay? I have to include C and D. I didn't include an F term here by construction of the problem, because that would just simply be saying something else physically is going on. Okay, so I have that. That's the psi continuous, the psi prime continuous, right? It's going to be K A minus B equals K prime C minus D. And then there's the X equals L. Blah, 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 blah. I'm not going to write them down, right? You've seen it, and there's nothing to be gained from me writing all that stuff down. So we solve. And you can see the book if you'd like to see the gory algebra, right? But you can imagine what the expressions are here, right? I hope there's no one unhappy that I'm not writing this down. No one's unhappy? Huh? What do you think? That's a good question. What do you think? Why would it be K double prime? Where does K come from? How do I find K? Should I have used K double prime here, say? But remember, what I'm doing is I'm plugging into the Schrodinger equation, the time-independent Schrodinger equation. Maybe I skipped too many steps. I'm plugging into that, which for psi being a constant, I'll write psi prime prime for d by dx squared. If u is a constant, it's just that, right? And so essentially there's just I'm just solving this twice. I'm either solving it for u equals 0 or for u equals u naught, right? And of course what I'm doing, if I say psi is some constant e to the ikx, then psi prime is ik times psi. And psi double prime is minus k squared, because it's ik times ik times psi. I'm plugging that in there, the minus signs go away, and I'm getting k squared a squared over 2m equals that. Boom, boom, boom. You should be able to whip that out. I keep saying it, right? So no, I don't want to use k double prime because, in fact, u is 0 out there. Okay. Would anyone like to see me write down the x equals L conditions? No. Okay. So if I solve, what do I find? Some algebra. I work, and then I get I've splintered my chalk. Let's see what happens here. R equals, okay, sine squared K prime L over sine squared K prime L. That's clear. That's going to come from this boundary, right? I was going to have C I K prime L plus D E, the minus I K prime L equals other stuff. And then there's another term here. I'm going to call it kappa. You know, kappa was some mess. It was K squared, K prime squared over K squared minus K prime squared squared. Okay? So this is unitless, and that's unitless. And the transmission, well, do I expect that R plus T is going to be 1? Let me ask two questions about this. First off, what was R, just as a review? It is all this stuff, but what was the starting definition of R? You should be able to know this. What is it?
Flux of reflection.
Yeah, it's the flux of reflection, which is B star B times K, right? Which is going to cancel out over the incident flux, which is A star A times K. And then that happens to cancel out. And what was transmission? It's the final flux, which is E star E. And again, the K is going to cancel out over the incident, okay? In this case, none of A or B or E will have to be complex. It will be complex if I have the tunneling situation, because then I'll be mixing. Here, when I take a derivative on everywhere, there will be an I and it'll cancel out. But if I'm going to have the energy less than U0 condition, I'm going to be mixing alphas and IKs. Anyway, should I have reflection plus transmission equal to 1 again? Why not? Well, okay, so first off, is it tunneling in the barrier? It's not really tunneling. And I'm not just trying to be nitpicky here, right? If the energy is greater than U0, I have nice well-defined sine waves there. And it's not the classically forbidden region.
Yeah, sorry, I was thinking E below.
Yeah. You were thinking E below.
It's because D should be
Well, C and D are both non-zero. It's well behaved. There's nothing funny. E is greater than U0. The kinetic energy is positive here. I should get the, yeah?
Is it possible you could have some sort of analogy to total internal reflection that bounces off the one barrier and bounces off the other barrier? Continually does that.
Yes. Okay, but that's not going to change the fact that R plus T is 1. All right, and I should know that, because I mean, if I look at the thing from from 30,000 feet, so to speak, I have a flux coming in. Some could bounce back. Some amount of the flux is contained in this region here, but it's traveling through, either in the forward direction or in the backwards direction. Okay? And this sort of causal thing, which you were asking about, which is interesting to think about. I mean, do I actually have a particle come in, reflect back, Zeno's paradox style, boom, 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 boom? Yes, in principle, in some sense, but in fact, when I just solve this thing, I'm solving for a static picture, but that includes motion, right? So what we've set up here is waves always coming in, always leaving, always reflecting. The whole thing is going on at once, and it's all just steady fluxes. We're talking about a stream of water doing various things, but it's just a current, if you will, okay? And the fact that there's some current in the hump region doesn't change the fact that at the end of the day, if I have stuff coming in, I better look at what's leaving and what's coming back, and that ought to sum to 1. I could also define some coefficient that describes the amount in here, and it should be sensible, but it's not going to change the fact that r plus t is 1. Okay, and if r plus t is 1, what ought to t be? In fact, shouldn't it be kappa over sine squared k prime L plus kappa? Yeah.
So that reflection then is a total reflection, like it includes reflection from, meeting and reflection from possibly going down back to zero.
Absolutely. And you don't see that, right? We just solved the whole thing at once, and it's going to include all that physics, right? How mathematically is it including all that physics? The way it's including all that physics is these conditions I didn't write here. I mean, I can't, sorry, if I write, when I write these two terms down, I don't have enough to solve for all these constants. I got 4 unknowns so far. How many equations do I need? Oh, in fact, wait a minute. That's a whole other discussion. The point I was trying to make was simply that I need both boundary conditions to solve fully. I can't even find B without writing down both boundary conditions. There's not enough equations and unknowns. That means that I was including reflection off of this second barrier effectively. All right? Although it's kind of hard to see like as a mathematical thing, but just the very fact that I needed to account for both barriers to get all of the, to find all my constants does say that. And yeah, let me go back and say, what about, let's count boundary conditions and unknowns. I had A, B, C, D, E, 5 unknowns. Now, when I have all 5 of those, is really, there's some sense, a normalization condition. We can't normalize a plane wave, we just divide by it. So if you want, you could just call A equals 1. But I really only have 4 unknowns that I really care about, because I'm always going to be constructing ratios. And then indeed I had 4 equations. Psi and psi prime continuous at the 2 boundaries. So that makes sense. Can I get an energy? I'm going to get an energy condition. Remember, I got energy conditions sometimes. I don't get an energy condition. All right, that only worked out for bound states. That I got a condition on the energy which led to quantization. All right, that's only for bound states. And it plays out here. It will always, if you've done things right, that will always work out also matching the number of unknowns in equations. So in other words, if you solve a bound state system, if this were somehow a bound state, basically, there was a well here in 2, and in 1 and 3 you didn't have a well. More or less, I would have to cancel one of the 2 terms over here, because only one thing would be allowed out there, it's decaying, and one thing out here, because it's decaying. I would have 1 fewer term then, but I would still have the same number of boundary conditions. But that would amount to 1 extra boundary condition was giving me this condition on energy, which was set the quantization of the energies. Okay? It's useful to keep this all in your head when you're trying to solve problems. It will always work out if you've set things up right. Okay? And in fact, that's the right answer. I just guessed, I just deduced t from this. Right? You can see that this is the thing I have to add to that just to get the numerators to sum to equal the denominator. But if you solve it fully, you'll explicitly find that. Okay? So you could say that I could derive that by fully solving and finding those 2 things. Okay? And then there is one interesting point here. So this question about, you asked about total internal reflection-ish idea. There is an idea here. Look at the numerator for the reflection coefficient. That has zeros. Notice that. So r, which is proportional to sine squared k prime L, well, and it has some stuff in the denominator, but the denominator kappa is positive always, so ignore that. Just look at the numerator. This is equal to 0 when k prime L equals n pi. And n is here 0, 1, 2, etc. Okay? Right, and what does this imply? Let me see, this is saying 2 pi over lambda prime L equals n pi, which is to say, you know, where lambda prime is the wavelength associated with this k. This is to say L equals, the pi's cancel, and just rearranging, lambda prime over 2 times n, and then n is these values. So that's basically saying, if here's the barrier, lambda prime is the wavelength of the wave in this region of the barrier, and if half the wavelength, the smallest, well, n equals 0 is kind of a trivial, is one possibility. The next possibility is n equals 1, so let's say lambda over 2 just fits in the barrier. So that's to say it's like that, right? Okay. In fact, n equals 0 is nothing. That's saying k prime is 0, which is not, it does, yeah, that's no energy. That's the no particle state. So it's n equals 1, 2, 3, etc. So it's like, so basically, it's saying how many integer half wavelengths fit in here. So indeed, that is exactly a resonant condition. So if the wavelength is just exactly equal to, half the wavelength exactly fits in the barrier, there's no reflection. That basically must mean that the reflection off this front face and the reflection off this back face must destructively interfere. Okay? And so there's conditions like that. And in fact, I don't know if you know this, but sophisticated optical elements, like sunglasses, which actually can be quite sophisticated if you buy expensive ones, have layers of coatings that do this same sort of trick. You can arrange optically to have reflection being exactly 0 off of any reflective coatings. They act just like this, and the mathematics is exactly the same. You arrange so that the reflection off the front and back of a coating exactly destructively interfere. Okay? And it's the same sort of idea. Okay. So that's that system. Now, and now, you know, so that's amusing. The particle has these, it's certainly not classical that you have these, you have this resonance in the reflection and the transmission, although it's classical for a wave, but not for a particle. Now let's just consider the case of the potential being higher than the energy. U0 is up there. This is the same. That's the same. But here, right, I can't have the exponential, the oscillating solutions. I have these static solutions with an alpha. And by changing the sign there, I take into account that effectively I've changed the sign when I collect terms in the Schrodinger equation, right? So I have decaying terms or growing terms. Once again, even though my instinct might be that I can't have this growing term out here towards positive x, because this thing does not grow to infinity, I by no means can just toss it out, right? You can only say c is equal to 0 if the barrier is going out literally to infinity. In fact, even if it gets very, very wide, if you throw this term out, you get nonsense. You have to have both terms, okay, mathematically, or your boundary conditions will get all screwed up, right? So, right, that boundary condition becomes like this. The next condition is just like these, except the exponentials go along for the ride. And once again, I won't solve, but I'll write down the answer. This becomes sinh squared, which is the, you know, the hyperbolic sign. I mean, it's not so surprising, right, that there's a very simple change from from the behavior in the previous problem to now, but it's not completely the same. This is 4y times 1 minus y, where y is the energy over u0. Just a fraction of the energy of the potential. Y hitting 1 is where you're just exactly able to overcome the barrier. This will be defined the same. The transmission condition, basically, well, you can see there's just it's almost the same. It's the same sort of changes. Or are you guys laughing because you can't do this in your... Well, no, you're supposed to rewrite it. Okay. But it's the same sort of, it's the same sort of equations, right? R plus T is 1 again, etc. Okay? Now, of course, here's the interesting thing. T is not equal to 0. So again, let's think of the classical analog. This is like saying I have a hill like that, and I have a ball, and I give the ball some kinetic energy, and it's gonna, and there's a hill here of potential, mgh, and the hill is bigger than the potential energy is bigger than the kinetic energy. And classically, the ball would come up and roll back. Quantum mechanically, that will happen with this probability, which if you think about it a bit, if alpha L gets big, this is going to go to 1, okay? But there's still this finite probability for this, okay? Let me erase that. Let me move the y over. In fact, let me just simplify the board here. You knew that. I already told you that part. Y was equal to E over U0. So this term up here, it's got y and 1 minus y. If y is small, it's essentially 4y over sinh squared. Okay? It's not 0. So it's as if the ball comes and rolls up the hill and then suddenly spontaneously pops over to the other side and goes out. Right? So this is called quantum mechanical tunneling. It is classically forbidden. The ball somehow, I think there's not 2 L's in tunneling. The ball somehow managed to go through a region where it had negative kinetic energy. And it just went through and came out the other side. All right? And there is absolutely no classical, explanation for this effect. Okay? There actually is an analogous effect of frustrated total internal reflection in optics. But there it's just like, some behavior about a wave that was already a wave. Not quite as mysterious, I think, or puzzling in a way. So this is a purely quantum mechanical effect. This is a bit of a mouthful, right? But sinh squared is like think of the exponential formula for the Euler's formula version of sine and cosine. Sinh is that, but where everything is not e to the I theta, but e to the alpha L. So if alpha L grows bigger than 1, this term dominates over that because y is very small, and this is an exponential, and there's a part of it is growing, and this goes to 16. Sinh squared becomes 2 exponent, and so this becomes 16y times 1 minus y e to the minus 2 alpha L. Okay, you can see that that's a straightforward extrapolation. Or let me just say it's approximately equal to that. And here's the key point. It's that. It's exponential in the barrier. It's exponentially suppressed. Okay, this is also can be small, e less than u0, but that's not an important term. That's a big term. And you need to remember that. That's just a basic fact. If you have a tunneling process, the probability is simply exponentially suppressed. Okay? So now there's two practical examples of this we should discuss. And one I gave a couple of homework problems on. That's alpha decay. So if we have a heavy nucleus, this is uranium or thorium. Some of the isotopes of lead do this. And it's got some Z and it's got some, where do I want to write this? Some Z, some A. For reasons I'll describe later in the semester, it's energetically favorable to end up with Z minus 2, A minus 2, and the Z equals 2, A equals 2, which is the helium-4 nucleus, separate. Okay? So if you remember, this is saying, basically I'm saying a big nucleus with some number of protons, plus neutrons, it will spontaneously spit out a object which is basically the nucleus of a helium atom, 2 neutrons, 2 protons. This is called an alpha. Just because back when they were discovering all this stuff and they didn't know what anything was, they called the first one they saw alpha, the alpha ray. The second one, a beta ray, which was later renamed as an X-ray. And the third one, a gamma ray for alpha, beta, gamma, which turns out to be a photon. Okay? And so this is a common type of radioactive decay. All right? Now, if this is energetically allowed, the reason it's allowed is basically, it's a little bit subtle, and I don't want to go into it because I'm going to spend time on it later in the semester, but just, this is energetically a lower energy state to get rid, basically, when nuclei get too heavy, they become unstable. Okay, and we'll talk about the reasons for that. This is a slightly smaller guy, and this is a very stable, tightly bound nucleus. So that's the sort of favored thing. If I'm going to split up a little, the nuclei that do this, some of them anyway, certain elements, certain types of uranium and thorium, also can spontaneously have fission, which is how you get nuclear power and nuclear bombs. Okay, but even those guys that do that, they more readily do this. But you might ask, if this is energetically favorable, why doesn't it just happen right away? And it doesn't happen right away. Some of these decays, the nucleus can, for the case of uranium-238, the half-life for this, which means how long it takes on average for something to decay, roughly, is 4 billion years. So why doesn't it happen right away? Well, it turns out that the intermediate state, right before it splits apart into two, this has a high surface tension, if you will. And the nuclear strong force. And that's an unfavored state. Right when it's just starting to split, there's a high surface energy associated with that. And if you don't like that, well, just wait till the end of the semester and I'll talk about it in more detail. But for here, I just want to say, look, the way that is modeled is the following. You say that it has a potential versus separation x of the alpha and the big nucleus. So in other words, I think of that x as the distance this little proto-helium nucleus is separated from the alpha, and 0 will be if it's right there in the center. sort of at the edge of the nucleus, it has this enormous force. Well, this is potential. This is potential energy. It has a thing like that. So it's just a barrier. It's just like I drew at the beginning of the lecture. Okay, although the real shape is a little closer to what I just drew. And just to remind you, when you draw potentials, right, a force is minus, the force in the x direction is minus du dx, right? So what's the force here? This can't actually be infinitely steep. It has to have some slope. This is a force that way, and this is a force that way. Because this is a positive slope, but there's a negative sign in the definition of force. And there's a negative slope, and there's a positive sign in the definition of force. There's actually a force over here, because once this guy gets a little ways away, this is an enormous electrical charge, like 80 in the case of lead, or 90 in the case of uranium. And this has a charge of +2. So electrically, bang, it gets shot away. That's this slope. This thing here, which is a strong force back that way, is a mapping of the force that's reflected in the surface energy to get to this deformed state. All right. That's a kind of qualitative description of alpha decay. But the main point is it's a barrier. And you can think of the kinetic energy of the alpha sort of being some number in here with sort of zero potential. That's the way you think of the nucleus. There's sort of no potential if you're in the center. Here, the kinetic energy would be less than zero because it's, though this is the total energy here, which is equal to kinetic energy in this region. It's equal to kinetic energy in this region. Here the kinetic energy is zero. Here the kinetic energy is finite, but not as, there's some potential. All right. And all right, that's interesting. Now, how am I going to relate it to this? Or in particular, what we talked about over there. So the fact is that this of all the neutrons and protons in here, if 4 of them can get together, they can make a break for it and escape. But there's a barrier. They can't get through the barrier. But quantum mechanically, they can. And the transmission probability is that. Okay? That's the transmission probability. We just discussed it. I mean, that was for, this strictly has to be modified because this is sort of this curved shape. And I solved this. This is a highly accurate approximation of the exact formula for the, the case of the exact square type potential. And, if I solve it completely, it's modified a little bit if I use this potential instead of that. But it's basically the same thing. And again, it's dominated by an exponential term here. However, I need a new concept. That's a transmission probability. Well, wait a minute. What did this transmission probability have to do with? That was I had an incident flux, and that was the amount out. And that's clearly, I'm not talking about that. I have one atom, and it just sits there, and then it eventually decays. So how do I relate concepts? The way we do it is we say the rate equals the number of attempts in some time frame. Okay, what's a rate? The rate is 1 over time. Right, that's a rate. The units of a rate is 1 over time. So the rate is the number of attempts in some time times t. The transmission probability, if you will, per attempt. I can interpret t that way. Essentially, if I think of this thing as it's basically a standing wave that's trapped here, which I can think of as plane waves going back and forth. And then it just whack, 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 whack. It keeps hitting, this proto-alpha particle keeps hitting the wall. And it just does it many, 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 many times. But there's some probability t ratio of an attempt to an escape. And eventually it escapes. And so this is the right formula. And what is the number of attempts per time? That ought to be, if you think about it, that's 1 over the transit time. In other words, if you get me really, really, really angry and I start running around the room and smashing into the walls, and just in a line though, I'm like sort of half in control, so I'm just running in a line, but I'm really, really angry. The number of attempts per time is 1 over how long it takes me. It takes me I'm so angry it takes me 1/10 of a second to run back and forth. I'm going to have 10 smashes per second, right? So it's just 1 over the transit time, which is 1 over a time is, let me see, it's the distance divided by the velocity. And if this is sort of the if this is the radius of the nucleus, and there's really 2 barriers, there's another one over there. This is the diameter, 2r, divided by the velocity. So this is the velocity over 2r times t, or that's just the, you know. Okay. And so I gave you a couple of homework problems where you work out results from this where you use this for t. Okay? And the answer is that this suppresses the probability enormously. Alpha L is a very large number. This is a very tiny exponential, such that even though it's energetically favored, uranium lasts 4 billion years. Okay? Thorium lasts about 1 billion years, etc. Although some of them are short. You remember the guy got poisoned by polonium the Russian guy? Yeah, that was that stuff has got a 138-day half-life, I believe. All right? And basically the difference between uranium and that stuff is basically just simply how high is this energy. Right? That's the powerful term. The energy matters because this is E over U0. But that's a negligible thing compared to alpha is that. And so if E gets close to U0, alpha gets smaller and you win exponentially in that. That's a much, much more powerful term. Any nucleus for which this is, alpha is small already decayed. It basically never formed. Okay. So I have one other thing to talk about. And so there's homework and whatnot on this. Now let me just talk about something I don't think I gave a homework problem on. And if I did, it would be the same mathematics. But this is just another interesting physical thing, and I'd like to tell you about it because it's neat. I've said a couple of times this semester that we've never seen an atom. Right? And in fact, if you use if your definition of the word seen means your eyes and photons, then the answer is yes, you've never seen an atom, nor will you ever see an atom, because an atom is so much smaller than a wavelength of light that you can't, it's not like a question of was the microscope adequate. If the light is so much bigger than the atom, you fundamentally can't see it, okay? However, we have imaged atoms. And I believe this is really about, well, okay, there's different ways of talking about it, but one of the most spectacular ways that we've imaged atoms is with a scanning tunneling microscope. Have you guys heard of this? They awarded the Nobel Prize in Physics for this right when I got to graduate school, and I guess right before you guys were born. In some sense, it's a fairly recent invention. Microscope. Okay? Binning and Rower, 1986, got the Nobel Prize for this. Okay, it's a cute little idea. I have some surface. This is some surface I want to look at. It's got to be a conductor, or it doesn't work. Okay? Electrical conductor. What you do is you take this tiny probe tip. This thing is literally something that ends up essentially being the size of an atom on the end. And there's a whole story about how in the world do I get like a tip of something that's, you know, sort of almost just one atom narrow at the end. But there's ways to do it, okay? And you apply a voltage between the two. This is also conducting. This is a conductor. It's metal or actually it could be a carbon nanotube at times, okay? But those conduct. And you put a voltage between the two. Battery, it's V. And current flows between the two. However, you might remember when we talked about the photoelectric effect that we talked about the fact, here's energy. If you have vacuum, or you could think of it, you know, some air being there, but actually this is done in a vacuum because you don't want the air interacting with the electron as it goes through here. So this is the vacuum. This is a metal or a conductor. Remember I talked about this? There's the work function. This is the energy of an electron. If it's here in the metal, there's a bunch of electrons with energies at some level or lower. This is, for technical reasons, called the Fermi energy. To get into the vacuum, the electron needs, you need to supply energy equal to the work function, okay? And so if that's my picture for this tip, basically, let me draw this same diagram sideways. There's some energy level in the tip over here, and then in the vacuum, there's the work function. In fact, let's, for simplicity, say these metals are the same. They don't have to be. Then the width would be a little different on this side than that side. But then you're back to being in the metal. Okay, so there's electrons here in energy. They need to get up to here and back down to there, but they can't do it. The voltage effectively supplies a little bit of energy, but not enough. I mean, if you put a huge voltage, you can make it energetically favorable so it will go. But in practical terms, you have a system where this is completely forbidden classically, but proceeds quantum mechanically. And once again, the tunneling probability has a term like that, right? So it's an exponentially suppressed thing. And in these situations, alpha times L is on the order of 100. So this is e to the minus 200, which is essentially 10 to the minus 100. Okay? And then if you change L by a factor of 2, I can change this from being 100 to 50, say. Okay? And so this e to the minus 100 changes to e to the minus 50, which is a huge change. That's changing from 10 to the minus 50 to say 10 to the minus 25. 25 order of magnitude change in the probability. So the current here is exponentially sensitive in the distance. And you actually bring the tip down to where it's really close to the surface. And then the current actually becomes finite and you measure it. Okay? And then you move the tip around. And by measuring the current, you map the surface. And if it's all just one material, that map is just the height. But then in fact, the tunneling current depends on a little bit on which atoms there are. And so you can actually tell things about the chemistry of the surface, like what is the material on the surface. Okay? There's one last concept here, which is you use feedback. Do you guys know about feedback? If you just brought the tip down, suppose I build a fancy apparatus. You can imagine actually what these are like. The tip narrows down to the size of essentially an atom. In practice here, it's only some number of atomic distances above the material. I mean, a few tens, but you know, really, really close. I mean, we're talking on the scale of a nanometer, right? Billionth of a meter, okay? And imagine having some apparatus and then you have some knob which is going to turn some motor which is going to make this tip come down. and you're sitting there like this, and you're looking at a current on a, a display screen, you're just going to smash the tip into the surface, your first attempt, your second attempt, all attempts. You'll never get it. What you use is a very, very powerful notion. It's actually from, in many technical fields, you use negative feedback. You don't try to attempt to control it. You measure the current, and you use the current to control the motor. Okay, and you put them what's called a negative feedback loop, such that if it gets too close and the current's increasing, you pull back. That's negative feedback. On the other hand, if it's going too low and the current is decreasing, you go the other way and you operate around some current you were shooting for. Okay, so then what happens is the tip goes along at a constant distance, the current's changing, and you measure the current. Or actually the current is held constant, the tip's moving around, and you measure the feedback signal that you fed to your system to keep the tip at the same distance. So it's a negative feedback loop. And that totally has revolutionized the notion of like looking at materials, right? And so you've seen these images maybe of atoms on surfaces. Actually, a guy that I went to grad school with, one of the first cool applications of this, he was probably, 26 or 7. He was working down at IBM, and they spelled out IBM in atoms on a surface. And it was covered in the New York Times, things like that. Moving the atoms around with this thing and then measuring it with that. And they spelled it out with single atoms. So it's a powerful technique and a very interesting one and very useful one. Okay, I'll see you guys Wednesday.